Risk Assessment Concepts for Risk-Based Inspection, RBI, according to API 580 Recommended Practice, Fundamental Principles Guiding Effective Inspection Strategies. Risk Assessment Concepts for Risk-Based Inspection, Presentation Agenda and Learning Objectives. The agenda for this presentation is structured to build understanding progressively, starting from fundamental concepts and moving toward practical RBI decision-making principles. First, an overview of risk-based inspection is provided to establish the purpose and scope of RBI within asset integrity management systems. This is followed by a clear definition of risk as used in API recommended practice, including the commonly applied risk equation that combines probability and consequence. The presentation then explores the two core components of risk in detail: probability of failure, POF, and consequence of failure, COF. Each component is discussed from an engineering perspective, including key influencing factors and how they are evaluated in RBI methodologies. After establishing how risk is assessed, the presentation addresses risk management and risk reduction, focusing on how inspection, mitigation, and operational controls are used to maintain risk at acceptable levels. A dedicated section explains the role of inspection in reducing uncertainty and supporting risk-informed decisions. The presentation then introduces the important distinction between relative risk and absolute risk, clarifying why API RBI methodologies primarily rely on relative risk ranking rather than precise numerical risk values. Throughout the presentation, emphasis is placed on practical application, alignment with API RP 580/581 guidance, and consistency with engineering best practices. The learning objectives are to enable participants to understand RBI risk terminology, explain how risk is evaluated and managed, and confidently apply relative risk concepts when prioritizing inspection and mitigation activities. These objectives support effective participation in RBI assessments and informed decision-making within multidisciplinary integrity teams. Overview of Risk-Based Inspection, RBI. What is risk? Definition and engineering meaning. Risk-based inspection is a systematic and structured approach used to develop inspection plans based on the risk associated with equipment failure. According to API RP 580, RBI integrates knowledge of materials, damage mechanisms, inspection techniques, and process conditions to assess where inspection resources will have the greatest impact on reducing overall risk. RBI does not eliminate the need for inspection, rather, it improves the effectiveness of inspection by focusing attention on equipment with higher risk profiles. In an RBI program, equipment is evaluated to identify credible damage mechanisms such as corrosion, erosion, fatigue, creep, and cracking. These mechanisms are then used to estimate the likelihood that the equipment will fail over a defined time period. At the same time, the potential consequences of failure are evaluated, including impacts to personnel safety, environmental release, business interruption, and repair or replacement costs. By combining likelihood and consequence, RBI produces a risk ranking that supports inspection planning decisions. AP emphasizes that RBI is an iterative process that should be updated as new inspection data, operating experience, or process changes become available. RBI is commonly applied to static equipment in operating facilities, including pressure vessels, piping circuits, heat exchangers, and storage tanks. When properly implemented, RBI supports safer operation, regulatory compliance, improved reliability, and optimized lifecycle costs. It also provides a transparent and auditable basis for inspection interval determination, which is especially important in high-hazard industries. In the context of API recommended practice, risk is defined as a measure of the potential for loss or harm resulting from a failure event. From an engineering perspective, risk answers three fundamental questions: what can go wrong, how likely is it to occur, and what are the consequences if it does occur. API RP 580 formalizes this concept by defining risk as the combination of the probability of failure, POF, and the consequence of failure, COF. This relationship is commonly expressed using the simplified equation, risk equals probability times consequence. While the equation appears simple, each term represents a complex evaluation involving engineering judgment, data analysis, and uncertainty management. Probability of failure reflects the likelihood that equipment will experience a loss of containment or functional failure within a specified time period, based on degradation mechanisms and inspection effectiveness. Consequence of failure reflects the severity of the outcomes associated with that failure, including impacts to safety, the environment, and business operations. Importantly, risk is not an inherent property of equipment alone, it is influenced by how equipment is designed, operated, maintained, and inspected. API guidance emphasizes that understanding risk in RBI is not about predicting exact failure events, but about making informed, risk-based decisions to prioritize inspection and mitigation efforts. This definition of risk forms the foundation for all subsequent RBI analyses and decision-making processes. Probability of failure, POF, consequence of failure, COF. Probability of failure, POF, represents the likelihood that a piece of equipment will fail within a defined period of time due to one or more damage mechanisms. In RBI, POF is not simply based on historical failure rates, instead, it is derived from an understanding of active degradation processes, material properties, operating conditions, and inspection effectiveness. API RP 580 and 581 emphasize the identification of credible damage mechanisms as the starting point for POF assessment. Common damage mechanisms include general and localized corrosion, stress corrosion cracking, fatigue, creep, and erosion. The rate at which these mechanisms progress is influenced by factors such as temperature, pressure, fluid composition, flow velocity, and metallurgy. Inspection plays a critical role in POF assessment by providing data on current equipment condition and reducing uncertainty about damage extent. The quality, coverage, and effectiveness of inspection methods directly influence the confidence in POF estimates. In many RBI methodologies, POF is categorized into qualitative or semi-quantitative levels rather than expressed as a precise numerical probability. This approach reflects the inherent uncertainties in degradation modeling and supports consistent risk ranking across large populations of equipment. Understanding POF enables engineers to predict how risk may change over time and to plan inspection intervals accordingly. Consequence of failure, COF, describes the severity of outcomes that may result if equipment fails and experiences a loss of containment or functional integrity. In API RBI methodologies, COF typically considers multiple impact categories, including safety and health impacts to personnel, environmental damage, and economic or business-related losses. Safety consequences may involve injury or fatality due to fire, explosion, or exposure to hazardous substances. Environmental consequences may include releases of hydrocarbons or chemicals to air, soil, or water, leading to regulatory penalties and cleanup costs. Economic consequences include repair or replacement costs, production downtime, and loss of revenue. COF is influenced by factors such as the type and quantity of fluid released, operating pressure and temperature, inventory, equipment location, and the presence of mitigation systems such as fire protection or isolation valves. API RP 581 provides detailed consequence modeling approaches, while API RP 580 allows for qualitative or semi-quantitative consequence assessment depending on the complexity of the analysis. Understanding COF is essential because even low-probability failures may require significant management attention if the consequences are severe. COF assessment ensures that RBI decisions appropriately reflect potential impacts, not just failure likelihood. Risk assessment process in RBI, risk management and risk reduction. The risk assessment process in RBI follows a structured sequence designed to ensure consistency and technical rigor. The process begins with defining the scope and boundaries of the RBI assessment, including the equipment population and operating context. Next, credible damage mechanisms are identified for each equipment item based on materials, process conditions, and industry experience. Probability of failure is then evaluated by considering degradation rates, remaining life estimates, and inspection effectiveness. In parallel, consequence of failure is assessed by analyzing potential release scenarios and associated impacts. The results of the POF and COF evaluations are combined to determine overall risk. Often represented using risk matrices or ranking systems. Equipment is then categorized into relative risk levels, such as low, medium, or high risk. Based on these results, inspection plans are developed to allocate resources where they will have the greatest risk reduction benefit. APA emphasizes that risk assessment is an iterative process that should be revisited when conditions change, inspections are performed, or new information becomes available. This structured approach supports defensible inspection planning and continuous improvement in asset integrity management. Risk management in RBI involves deciding how to address identified risks to ensure they remain within acceptable limits defined by the organization or regulatory requirements. Once risk levels are determined, management must decide whether the risk is acceptable, tolerable with controls, or unacceptable and requiring immediate action. Risk reduction strategies may target the probability of failure, the consequence of failure, or both. Reducing POF may involve improving inspection effectiveness, upgrading materials, applying corrosion control measures, or modifying operating conditions. Reducing COF may involve reducing inventory, improving isolation systems, enhancing fire and gas detection, or relocating equipment. Inspection is a key risk reduction tool because it improves knowledge of equipment condition and reduces uncertainty in POF estimates. API RP 580 emphasizes that inspection alone does not eliminate damage mechanisms but supports timely intervention before failure occurs. Effective risk management balances safety, reliability, and cost considerations, using RBI results to make informed, engineering-based decisions that optimize lifecycle performance. Relative risk versus absolute risk, key takeaways and engineering perspective. Relative risk and absolute risk are two different ways of expressing and using risk information in RBI. Absolute risk refers to a specific numerical value representing the expected frequency and consequence of failure, often expressed in terms such as events per year or monetary loss per year. While absolute risk can be useful in certain quantitative analyses, it requires high-quality data and precise models, which are often difficult to achieve in practice. Relative risk, on the other hand, compares the risk of one equipment item to another within the same system or facility. API RBI methodologies primarily rely on relative risk ranking to prioritize inspection and mitigation activities. This approach acknowledges uncertainty while still providing a robust basis for decision-making. Relative risk allows engineers to focus attention on the highest risk equipment, even if the exact numerical value of risk is uncertain. By ranking equipment from highest to lowest risk, RBI supports efficient allocation of inspection resources and risk reduction efforts. API guidance emphasizes that relative risk is generally sufficient for inspection planning and integrity management decisions. The key takeaway from this presentation is that risk assessment in RBI is a practical engineering tool designed to support better decisions, not to predict failures with absolute certainty. Risk is defined as the combination of probability of failure and consequence of failure, and both components must be understood to manage equipment integrity effectively. RBI provides a structured framework for evaluating risk, prioritizing inspection, and implementing risk reduction strategies in accordance with API recommended practice. Inspection plays a critical role in reducing uncertainty and supporting timely intervention, while risk management ensures that risks remain within acceptable limits. The use of relative risk ranking enables organizations to focus resources where they deliver the greatest benefit in terms of safety, environmental protection, and reliability. By applying these concepts consistently, engineers and integrity professionals can develop defensible, cost-effective inspection programs that support safe and reliable operation throughout the equipment lifecycle.